Somewhere in the sky, among the stars we see every night, there moves a visitor that will never return. It does not belong to our solar system, does not follow its usual rules, was not born near our sun. It is a traveler from another star, perhaps from another planetary system destroyed billions of years ago. We have called it 3I, Atlas, but behind that cold name lies an incredibly vivid story. A body of ice and rock that, as it crosses our cosmic neighborhood, appears to experience a slight, mysterious acceleration. When astronomers first traced its orbit, they immediately noticed something. It wasn't a closed ellipse like those of the planets, but an open path. A kind of curve that swoops in, bends around the sun, and then departs forever into interstellar space. That alone was enough to say that 3I, Atlas is not one of us, it wasn't born here. It is the third interstellar object ever observed passing through the solar system, after ʻOumuamua and Comet 2I, Borisov. But unlike ʻOumuamua, which appeared as a bare and fleeting point of light, 3I, Atlas revealed itself immediately as a true comet. A solid nucleus hidden inside a cloud of gas and dust, a spreading coma, and a tail stretching out into space, pushed away by sunlight and solar wind. Images from large telescopes show a luminous droplet suspended in darkness, with a slender tail growing longer day by day. It is not just a passing rock, it is an active, transforming object. The detail that stirs debate is this. When its trajectory is calculated using gravity alone, the pull of the sun and planets, the predicted positions do not perfectly match the observed ones. 3I, Atlas is slightly off course, as if it were experiencing a nearly imperceptible push beyond gravity. The push is minuscule, but it exists, and in astronomy, even a tiny discrepancy can ignite countless questions. This is where the concept of non-gravitational acceleration comes into play. To understand what that means, one must look closely at the physics of a comet. Imagine the nucleus of 3I, Atlas as an irregular block of ice, dust, and organic material, perhaps older than our entire solar system. When it is far from the sun, it is cold and almost motionless, a piece of darkness drifting among the stars. But as it draws closer, sunlight begins to warm its surface. The ice's water, carbon dioxide, carbon monoxide, and other volatile molecules don't just melt, they often pass directly from solid to gas, in a process called sublimation. These gases don't escape uniformly across the surface. There are exposed regions, cracks, fissures, and areas that absorb more heat. From these, real jets form, space geysers spitting gas and dust grains into space at tremendous speeds. Each jet acts like a tiny rocket mounted on the comet's surface. It ejects material in one direction and pushes the nucleus in the opposite direction. If the jets were perfectly symmetrical, their thrusts would nearly cancel out. But in an irregular, rotating body that heats unevenly, the total is never exactly zero. It is precisely this slight asymmetry that produces non-gravitational acceleration, a small, constant course correction. In the case of 3I, Atlas, studies suggest that much of this thrust may come particularly from very volatile ices such as carbon dioxide and CO, which sublimate at lower temperatures than water. This means 3I, Atlas can start breathing out gas and dust even at distances from the sun where many local comets remain almost silent. Space instruments observing it in infrared and ultraviolet confirm this. An extremely active object, with a coma rich in gas and a carbon dioxide to water ratio far higher than the average for solar system comets. Not only that, the light it emits tends to be bluer than usual, a sign that gas contributes more than dust to its overall brightness. This behavior is more than aesthetic, it's a clue to the physics behind its acceleration. Another fascinating clue comes from radio telescopes that have detected traces of the O radical, which forms when ultraviolet light breaks apart water molecules. It's a typical signature of active comets, telling us how much water is evaporating from the nucleus. In 3I Atlas's case, the amount is enormous. Large quantities of gas are expelled into space every second, as if a mountain of ice were slowly evaporating under the sun's heat. All this escaping material acts as a natural engine, though its power is laughably small compared to anything we'd imagine for a spacecraft. Numerically speaking, the thrust is minuscule. If we could stand on the surface of 3I Atlas, we would feel nothing. The acceleration from the jets would be far weaker than the pressure of the wind on our skin here on Earth. Yet, in the vacuum of space, without friction, even such a feeble force, applied over weeks and months, is enough to measurably alter the overall trajectory. A millimeter per second today, another tomorrow, and over time, the difference accumulates. Someone might ask, could it be something else? Could it be, for instance, a natural solar sail, an ultra-thin object pushed by sunlight? Or, since this idea always resurfaces with interstellar objects, could it be something artificial? In the case of ʻOumuamua, the very absence of a visible coma led some researchers to propose more exotic scenarios. But 3I Atlas tells another story. Here, the coma is unmistakable, the tail is evident, the gases are directly measured, the water's signature is seen at multiple wavelengths. Everything points to a far simpler explanation: ice evaporating, gas escaping, nucleus pushed, acceleration arising naturally. This does not mean astronomers agree on every detail. Precisely measuring non-gravitational acceleration is not easy. The nucleus is hidden within a bright cloud, and finding the exact center of that light in images is not straightforward. Small systematic errors can make a weak push appear significant. That's why studies differ slightly. Some find a clear net acceleration, others are more cautious, suggesting that within the margin of error it might be weaker. Yet the overall picture is clear. 3I Atlas behaves like a very active interstellar comet, and any extra acceleration, if present, fits perfectly with what we'd expect from an irregularly outgassing object warming in sunlight. It's not a maneuver, not an intelligent correction, not a sudden turn toward Earth. It's the breath of an ancient cosmic iceberg that, passing near the sun, flares to life for a moment before fading back into darkness. To fully understand how fascinating 3I Atlas truly is, it helps to compare it with the other interstellar visitors we've already encountered. 2I Borisov was, in a sense, reassuring. A comet straight out of the textbook, with a vast tail, plenty of dust, and a dynamic behavior that could be easily explained through classic outgassing. ʻOumuamua, on the other hand, was its exact opposite: no visible coma, strange variations in brightness, and a small extra acceleration difficult to attribute to jets that, for all intents and purposes, were invisible. 3I Atlas lies somewhere in between. It's interstellar like them, but its cometary nature is obvious. It shows gas, shows dust, exhibits every sign of a volatile rich object in full activity. Some estimates suggest that it may be larger than ʻOumuamua, and perhaps even larger than Borisov, with a nucleus that could reach several kilometers in diameter. If that size is confirmed, we're talking about a massive body, large enough to contain the history of an entire evaporated planetary system. Yet, the larger the object, the harder it is to accelerate. The more mass you have, the greater the force required to change your speed. The fact that 3I Atlas's outgassing still manages to produce a measurable deviation is a sign of how energetic the sublimation of its ices must be. It's as though beneath the surface lie vast reservoirs of CO and carbon dioxide, ready to burst into gas as soon as sunlight penetrates deeply enough. Each breath from these jets removes a little material from the nucleus and, at the same time, gives it a tiny push. Behind this behavior lies its history. An interstellar object like 3I Atlas hasn't merely spent a few million years drifting through space. It has likely traveled for billions of years, far from any star, immersed in near absolute cold and constantly bombarded by high-energy cosmic rays. This bombardment penetrates meters below the surface, breaking molecules, recombining them, slowly transforming the original ices into something new. It's possible that the outer crust of 3I, Atlas, is the product of this long, cosmic cooking, a layer tens of meters thick, made of altered ices and complex organic materials. When the sun heats it, we no longer see the primordial material it was born from, but this evolved crust, already shaped by interstellar time. The distribution of volatiles within it can be highly irregular. Regions rich in carbon dioxide here, pockets of CO there, channels of frozen water deeper below. As the nucleus rotates, the sun illuminates different areas. Some of these pockets heat up, internal pressure rises, and natural vents burst open, the jets. Each jet is an impulse of thrust, and the sum of these impulses, distributed over time, produces the observed acceleration. This situation makes 3I, Atlas a perfect natural laboratory. By precisely measuring how its trajectory changes and comparing that data with thermal and structural models, astronomers can reconstruct, at least in part, the distribution of ices on its surface. It's like performing a remote CT scan on a celestial body we will never see up close. We can't send a probe to orbit it, we can't collect samples, but we can use its acceleration as a signal to infer what's happening inside. As it loops around the sun on its hyperbolic trajectory, 3I, Atlas passes both in front of and behind our star relative to Earth. This makes observation tricky. At certain times it's too close to the sun in our sky for optical telescopes to track it. During those periods, however, probes and observatories positioned elsewhere in the solar system can step in. Some spacecraft orbiting Mars or traveling toward Jupiter may have better viewing angles when it's invisible from here. Every additional piece of data helps refine the acceleration models and determine whether the thrust decreases or shifts direction as its activity wanes. And, of course, there's the question everyone asks: is it dangerous? Whenever a large object crosses the solar system, someone wonders whether it could pose a threat to Earth. In the case of 3I, Atlas, orbital calculations show that it doesn't come nearly close enough to our planet to present any risk. Its path is well determined, and the non-gravitational acceleration it experiences isn't remotely strong enough to bend its trajectory toward us. It might slightly change the exact point where it passes, but we're still talking about vast distances on a planetary scale. Perhaps the most fascinating aspect of 3I, Atlas is that it forces us to rethink what we mean when we say, comet. For many years, we've studied those from the Oort cloud and the Kuiper belt, objects that, though ancient, were born within the same environment as our solar system. With interstellar objects, we are finally beginning to glimpse fragments of other systems. Comets born around other stars, expelled during violent phases of planetary evolution, cast into the dark, and left to wander. Every difference in composition, every unusual behavior, every deviation in trajectory is a clue to that distant past. The ratio of water to carbon dioxide tells us something about the temperature at which its ice is formed. The presence of certain organic compounds hints at the chemistry that reigned in its original protoplanetary disk. Its thermal response to the sun, how and when it lights up and fades again, traces the evolution of its crust under billions of years of cosmic radiation. And non-gravitational acceleration, which might seem at first a nuisance for orbit calculators, is actually one of the most valuable keys for deciphering all this. It's the direct signature of internal activity. Without seeing the jets up close, we can infer that they exist, where they are concentrated, how intense they are, and how they change. If, in the coming years, we discover more interstellar objects, and that's likely, given the rapid improvement of astronomical surveys, we'll be able to compare their accelerations, activity levels, and compositions. We'll find out whether 3I, Atlas is an extreme case or simply one of the many possible faces of interstellar comets. When its passage is over, 3I, Atlas will drift away forever from our sun, carrying with it secrets we'll never fully know. Its cometary activity will fade, the jets will fall silent, the non-gravitational acceleration will become negligible, and only gravity will guide it. But in astronomers' databases, numbers, curves, and graphs will remain, records of its position, its light, its speed. And within those records will lie the answer to the question we asked at the beginning. Yes, 3I, ATLAS has shown signs of an acceleration beyond gravity alone. Exactly what we'd expect from a very active comet. This acceleration isn't magic, isn't an alien engine, isn't a guided course. It's the natural result of evaporating ice, escaping gases, and the irregular structure of an ancient object shaped by time. It is the delicate yet readable signal of the breath of an interstellar traveler who, for one brief moment in the history of the cosmos, crossed paths with our sun. If you've made it this far, it means you love curiosity as much as we do. If this journey inspired you, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.